Welcome to Mythosium, the channel where we take ideas that seem impossibly complicated or deceptively familiar and break them open until the hidden structure becomes clear. Today we're going to explore one of the most iconic numbers in all of mathematics, a number that many people think they already understand, but which turns out to be more mysterious, more far-reaching, and far more transformative than its simple definition suggests. Most of us encounter pi for the first time as the ratio of a circle's circumference to its diameter. It's presented as a straightforward geometric fact, almost something you could measure with a piece of string and a ruler. But the deeper you go into mathematics, the more astonishing pi becomes. It's not just the number of circles. It doesn't live only in geometry. Instead, it shows up in the behavior of waves, the laws of probability, the structure of complex numbers, and even formulas that seem to have nothing at all to do with curved shapes. Pi is less like a measurement and more like a portal, one that leads into some of the deepest and most unexpected regions of mathematical thought. To understand why pi became such a profound object of study, it's useful to begin with a simple question. How do you measure the exact length of a circle's boundary? Humans struggled with this long before modern mathematics existed. You can measure a straight line exactly. You can measure the sides of polygons exactly. But a circle has no corners. Its boundary is smooth and continuous. So how do you capture that smoothness with tools that are fundamentally discrete? Early approaches involved approximating a circle using polygons. If you draw a hexagon inside a circle, it touches the boundary. Draw one outside, and it surrounds the circle. These two shapes give lower and upper bounds for the true circumference. By increasing the number of sides, the bounds tighten. In principle, with infinitely many sides, the polygons would converge perfectly to the circle. But in practice, increasing the number of sides becomes extremely tedious, and progress slows dramatically. Even doubling the number of sides repeatedly doesn't produce meaningful precision without enormous effort. This method was ingenious for its time because it provided a way to trap pi between two values. But it also revealed a limitation. Geometry alone makes slow progress. As mathematicians pushed this technique further and further, they encountered diminishing returns. Each improvement required disproportionately more work. It became clear that a new way of thinking was needed. That new way arrived when geometry began merging with algebra. Rather than describing shapes solely through diagrams, mathematicians began expressing them with symbols and equations. A circle could now be written as an equation. Its boundary was not just a curve you draw, but a set of coordinates that followed a precise rule. Once shapes could be expressed algebraically, they could be manipulated, studied, and broken down into smaller pieces. This shift opened the door to calculus, and calculus changed everything about how we understand pi. The revolutionary insight behind calculus is that even the most complicated curves can be understood by slicing them into infinitely small pieces. A curve may bend overall, but if you zoom in far enough, it behaves almost like a straight line, and straight lines are easy to measure. With this idea, people realized that you could analyze curves not by trying to measure them directly, but by breaking them into infinitesimal components and understanding how those components assemble into the whole. This was a conceptual earthquake. Suddenly, mathematicians could derive relationships between changing quantities. They could analyze slopes, areas, and arcs with unprecedented precision. And because the circle is one of the simplest curves, it became a natural testing ground for these emerging ideas. Instead of approximating the circumference with polygons, it became possible to represent the circle through analytic expressions, formulas that could be expanded into infinite series. The first infinite series for pi might seem puzzling at first glance. It expressed pi as the sum of infinitely many fractions. The series converged slowly, but it was a breakthrough. It meant that pi could be expressed using algebraic operations rather than geometric approximations. No shapes required, no polygons. Just a formula, endlessly unfolding, bringing pi into sharper focus with each additional term. But that was only the beginning. Once mathematicians realized that pi could be expressed as an infinite series, they found many more, some converging slowly, some astonishingly quickly. These series didn't merely compute pi. They revealed something deeper about its nature. They showed that pi isn't tied to the geometry of circles alone. It's woven into the structure of analytic functions, especially those involving periodic motion. This discovery was surprising. Why should the number describing circles appear so naturally in the study of waves, oscillations, and vibrations? The answer lies in the connection between circular motion and repetition. Anything that repeats itself, whether it's a swinging pendulum, a sound wave, a rotating object, or even fluctuations in electrical signals, can be described using trigonometric functions. These functions, sine and cosine, are built directly from the geometry of a circle, When you use them to describe motion, pi emerges automatically, because pi describes the fundamental structure of rotation. Pi, therefore, became much more than a geometric constant. It became the key to describing periodicity, the regularity and rhythm found throughout the natural world. Waves, cycles, and oscillations of every kind are stamped with its presence. This shift in perspective revealed that pi is a universal constant not because of circles we draw on paper, but because of patterns embedded in the universe. As mathematics expanded further, especially into the realm of complex numbers, pi's role grew even more significant. Complex numbers introduce a new dimension to math, allowing us to describe rotations and scaling in a unified way. Within this system, exponential functions can be used to describe circular motion, and when these functions interact with imaginary numbers, a remarkable identity emerges, one that links pi with the exponential function, -1, and imaginary units, all in a single equation. This formula seems almost magical, but it reflects something fundamental. Pi is not just a number, but a structural element of how continuous change operates in mathematics. The more these ideas developed, the clearer it became that pi appears in left places that, at first sight, have nothing to do with geometry. Pi governs the shape of probability curves. It appears in integrals describing random motion. It emerges in physics when analyzing the spread of heat, the motion of particles, and the distribution of energy in matter. It is embedded in quantum mechanics, field theory, and statistical mechanics. The deeper mathematicians looked, the more inescapable pi became. This raises an intriguing question. Why this number? Why not some other value? What makes pi so fundamental that it surfaces across such diverse mathematical landscapes? One perspective is that pi reflects something about how smooth, continuous structures behave. Whenever a system involves smooth transitions, repetitive cycles, or rotational symmetries, pi appears naturally. Another perspective is that pi reflects something about the constraints of mathematical relationships themselves. When you build systems of equations that describe change, the TPI becomes a necessary part of the solution. It's as if pi is not chosen by nature, but inevitable. As modern mathematics embraced computation, the study of pi took another leap forward. Infinite series gave way to algorithms capable of computing millions of digits. Later algorithms emerged that could compute billions and then trillions of digits. Each new method revealed deeper patterns in numerical behavior and pushed computing technology forward. The quest to calculate more digits became a benchmark for testing new hardware, new programming ideas, new algorithms, and new understandings of computational efficiency. What's fascinating is that while the number of known digits exploded, the practical need for them did not. Engineers can safely use just a handful of digits for almost every real-world calculation. Physicists rarely need more than a few dozen for even the most sensitive experiments. The effort to compute trillions of digits is not driven by necessity, but by curiosity. P has become a proving ground for the limits of mathematical computation, an arena where both math and engineering test their boundaries. Along with these computational achievements came new philosophical questions. Do the digits of pi contain hidden patterns? Does pi encode randomness or structure? Does its infinite expansion contain every possible sequence? The mysteries surrounding its digits continue to fascinate people because they offer a glimpse into infinity, something humans can compute piece by piece but never fully grasp. Even though trillions of digits are known, no repeating cycle has ever been discovered, and no definitive proof confirms the randomness of its digits. As the methods for analyzing pi grew more advanced, mathematicians uncovered even more ways in which pi connects distant branches of mathematics. It shows up in number theory, in combinatorics, in geometry on curved surfaces, in mathematical physics, and in the analysis of dynamical systems. Almost any area of advanced mathematics contains a doorway that eventually leads back to pi. And what's remarkable is that these connections are not forced. They appear naturally, emerging from the underlying structure of the systems being studied. This web of connections suggests something profound. That is not merely a number we discovered. It is a number that reveals itself when we explore the fundamental rules of mathematics. It's a reflection of the coherence and unity of mathematical ideas. Even though math spans countless fields and concepts, pi serves as a common thread, weaving them together into a unified tapestry. One of the most powerful lessons from the story of pi is that progress in understanding often comes from shifting perspectives. Early attempts to measure the circle directly were limited, but when mathematics embraced the idea of representing shapes through functions, the problem became richer. When algebra and geometry merged, new methods emerged. When calculus exposed the behavior of curves through infinitesimal processes, pi became accessible through new tools. When complex numbers expanded the scope of mathematical relationships, pi stepped into an even broader role. Through each shift, pi didn't just adapt, it revealed more of itself. This transformation mirrors how scientific understanding grows. Ideas evolve, methods refine, and constants that once seemed simple become windows into deeper truths. Pi serves as a reminder that even familiar concepts can hold endless layers when explored through new frameworks. It shows that human curiosity, pushing beyond the immediate and obvious, can unravel complexities that once seemed impenetrable. The journey of pi is not just a mathematical achievement. It is a story about the evolution of thought. It reflects how abstraction can lead to deeper insights, how intuition evolves with new tools, and how problems that seem narrow can open up into entire landscapes of discovery. When people first tried to measure circles, they could not have imagined that they were opening the door to calculus, complex analysis, modern algorithms, and theories that describe the fabric of the universe itself. This is what makes pi extraordinary. It's not only a constant that defines circles. It's a constant that defines relationships. It shapes the language of wave motion, the behavior of probabilities, and the properties of mathematical transformations. It suggested the universe follows patterns that are elegant, coherent, and interconnected. And through its study, we've been able to glimpse that elegance in ways earlier civilizations could not have imagined. At Mythosium, we explore ideas like this because they show how deep and beautiful the foundations of science truly are. They remind us that familiar symbols and constants are often just the beginning, that beneath every common concept, there may be layers of insight waiting to be uncovered. If you enjoy diving beneath the surface of mathematics and discovering the structure that holds everything together, make sure to subscribe. There are countless mysteries left to explore, and together we'll continue unveiling them, one idea at a time. Thanks for watching, and stay curious.